Here's another topic that you saw both in Algebra 1 geometry and Algebra 2. You see it especially a lot in geometry as you deal with right triangles and have to do square roots in various equations. There's a definition of a square root that is critical that you understand, and it's given symbolically as this little statement here. However, the better way to see this is that the square root of a is b only if b is the thing that squares to make a. So what I would suggest that you want to learn is this. What is the square root? Well, it's the thing that squares to make. So what squares to make 36? It's a 6. And why? Well, here's a cop-out. By definition. By definition. Because 6 is the thing that squares to make 36. What's the square root of x squared minus 6x plus 9? Well, of course, it's x minus 3. Why? Well, because x minus 3 is the thing that squares to make x squared minus 6x plus 9. That's the definition. So in algebra, you start seeing more expressions like this. By the way, there's a little bit of a caveat about this that we should talk about later, but for now I'll just leave it at x minus 3. So there are a couple of rules that you have to remember for square roots and simplifications. You can't leave, you can always break a multiplication inside of a square root into the multiplication of individual square roots. By the same token, you can do the division of a square root of a division and break it into the division of the square roots. Now you can't leave a perfect square number inside of a radicand, and your denominator has to be a whole number. That's just the rules of it, sorry. And you're never supposed to have a radicand that's a negative. So there's the numbers that generally you'll be able to recognize and use all the way through all your simplification. Just 2 squared is 4, square root of 4 is 2. The thing that squares to make a 9 is a 3. The thing that squares to make a 16 is a 4, etc., etc., etc. These are the tricky numbers to remember. Multiples of 16. So if you care, just kind of notice and commit it to memory. 16 doubled is 32, then you see the rest of the multiples. And then the only one you really need to worry about, 36, is doubled to 72. Tripled would be 108, but you probably don't care about that. So what I always do is this, and you should be practiced at it just from 3 years of previous math courses. So if you want to pause and look at those instructions, you can, but I'm just going to sail into it. So I always choose the biggest number that that's a factor of 96. That's where that 16 times 6 would come in. Now, I always like to write the square root of the perfect square first, because this shows the flow of the radical simplification. Because 6 is simply 3 times 2, and there's no square factor, meaning a 4, 9, 16, 25, etc., that goes into a 6. That's how I know I'm done. Now, a lot of you might recognize that 96 is divisible by 4. And you might even go old school with it and see that it's 24. And if you call this the square root of 4 times 24, you would not be wrong. That would be 2 times the square root of 24. And you're not wrong, you're just not done. You haven't completely simplified, because I could now call the 24 of 4 times a 6 and call that square root of 24 square root of 4 times the square root of 6, and then the 2 stays in the stream. Square root of 4 is a 2, and then square root of 6, and then I could simplify those and get to that. So by choosing the biggest number at the outset, you always reduce your labor. So 25 times 5, if you're thinking money, 5 quarters is $1.25. So I'd call this square root of 25 times the square root of 5. I replace something with its equal. The square root of 25 is 5, the thing that squares to make 25. Typically, in your final answer, you don't state the arithmetic. You don't have to state it in the previous step either, but that's more common. Now, a lot of you might see 9 times 6 is 54, but did you know that 27 times 2 is 54? So, with that in mind, I'm going to call that, oh, wait a minute, that won't do me any good at all, will it? That would be important on a cube root, but it's meaningless on a square root, so let's back up. 9 times 6 is 54, and so this becomes square root 9, square root 6. I can replace the square root 9 with its 3 equivalent, and then I'm done. So, describe in words, by definition, what's the square root of 13? Well, you should say it's the thing that squares to make 13. So, what is the square root of 13 times the square root of 13? Why, it's 13. Why? There's my cop-out. By definition, I took the thing that squares to make a 13 and I squared it. So by definition, it has to make a 13. So the reason that's important is that when I get to what they call rationalizing the denominator, then that little definition of the square root of 13 or whatever it might be becomes important. You should always simplify what's inside your radical first. I just happen to recognize that 12 divided by 3 is 4, and the square root of 4 I know is one of those perfect squares, so it's 2. This one, not so much, so I have to call it the square root of 5 divided by the square root of 3. And I'm not allowed to leave a square root in the denominator. I might talk about that more in class. It's a stupid rule. You don't have to follow it when you get out of high school. But while you're here, you have to follow it. And on the ACT and the SAT, they follow that rule too. So the square root of 3 times the square root of 3 makes a 3. The square root of 3 is the thing that squares to make a 3. So I multiply by a form of 1. That's always what I do with a fraction. Then I do top times top, bottom times bottom. So I get square root of 15 over 3. That's considered a better form. If you put this into a calculator, or this into a calculator, or this into a calculator, you get exactly the same decimal approximation for them all. But this one is considered the better form. So notice that the rule says that the square root of AB is equal to the square root of A times the square root of B. Well, all I've done here, that was strange, is taken that rule in reverse. I've said the square root of 5 times the square root of 3 is the square root of 3 times 5. So that's how I got across the top line there. You multiply fractions just straight across, so that's what you get. Notice again that I can break fractions into the division of the numerator and the denominator, each in its own square root. Just so happens the square root of 16 is 4. If I didn't recognize that, you just make a bigger problem for yourself. If you did the square root of 16 times the square root of 5, you'd get a square root of 80, and you'd have to simplify that. So we like to simplify everything we can first, but notice the square root of 5 is the thing that squares to make a 5. So if I square it, if I multiply by itself, it makes a 5, period, by definition. So that's what I do here. I multiply by square root of 5 divided by the square root of 5, and I multiply straight across, but notice this time the 4 is just a coefficient, and it becomes 4 square root 5 divided by 5, and that's considered the simplest form. Now, in Algebra 2, you learned about the fundamental imaginary number. The fundamental imaginary number was introduced probably about 4 centuries ago to allow solutions to equations like this. And initially, scientists and mathematicians thought that the people that came up with this were stupid. Turns out that there's a whole branch of physics, especially alternating current electricity, that requires the understanding of imaginary complex numbers to represent current flow. It took several centuries before of using imaginary numbers before people realized that the imaginary number system perfectly modeled that form of electricity. So just goes to show, you never know. Anyway, with that in mind, the square root of negative 1 can't be 1 because 1 times 1 makes 1, not negative 1. And the square root of negative 1 can't be negative 1 because negative 1 is not the thing that squares to make negative 1. Negative 1 squared, negative 1 times negative 1 is 1. So you have to remember these two, that by definition the square root of negative 1 is I. Well, if I is the square root of negative 1, or I, is the thing that squares to make negative 1. So I squared is negative 1. What we typically do on something like this square root of negative 80 is we call that the square root of 16 times the square root of negative 5. And then if we went a little bit further, we'd say the square root of 16 times the square root of negative 1 times the square root of 5. Now that's a little bit extra work if you just recognize that square roots of negative always give imaginary answers. Then you would have just thought of this and said, well, that's going to be a 4 square root of 5, but because it's square root of a negative, it'll be an imaginary. And the custom is to put the imaginary on the left side of the radical. We don't like there to be anything on the right side of the radical just for confusion's sake. And if we have a letter, in this case I is not a variable, but it's a constant. It's a letter representing some number. Whenever we have a coefficient and a letter, we always like the coefficient or the number first and the letter second. So this is the preferred form of that. By the same token, I would recognize that 4 times 3 is 12. So I would think of this as 3 times an I times the square root of 4 times the square root of 3. And I recognize that the square root of 4 is a 2, so I would call that 6I square root of 3. And again, notice that I like nothing to the right of the radical, and I like the I in between the coefficient and the radical. Same way here, I see a negative 5, and then I'd see a square root of a 4 and a square root of 5 to make the 20, but because it's a square root of a negative, I know it's imaginary. So the square root of 4 becomes a 2. 2 times 5 is 10, so I get negative 10I square root of 5. So that's simple enough. Now, sometimes the problems that we're going to have to solve will involve us having to do some kind of complicated arithmetic. So you can stop and read these bullet points if you want to. I'm just going to keep flying. Negative 7 times 2 is negative 14. But I times I is an I squared. Please notice that that's the same principle as negative 7x times 2x, which would be negative 14x squared. The only difference is that if I ever see an I squared has a specific numerical value. Therefore, this is like negative 14 times negative 1, which is equal to positive 14. So by the same token, this would be negative 2 to the 5th times I to the 5th. Negative 2 to the 5th is negative 2 times negative 2, blah, 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 blah. If you do that out, you get a negative 32. But what about that I to the 5th? So what I see on I to the 5th is that it's I squared times I again. That would give us a negative 32 times a negative 1 times a negative 1 again times an I. So notice the negative 1 times negative 1 is a positive 1, and then times the negative 32 would be a negative 32I. So simple as that. Treat these problems that look like distributive rule like distributive rule. So 3I times 2 is 6I. 3I times negative 5I is negative 15I squared. But as you create that I squared, remember that I squared is a negative 1. So we now call this 6I. And a lot of you know this trick from Algebra 2. A lot of you would realize that that's simply going to be a sign switch. I'll show all the steps this time. That's negative 15 times negative 1, which then becomes 6I plus 15. And a lot of you would recognize that we could have skipped this rewriting here. Now, one of the things, it is not wrong, but it is customary always when I have a complex number to write the real number component first, the 15, and the imaginary component second. It's not wrong if you don't, but you'll probably get some blue ink on your paper if you leave it in that order there. I'm going to do this like a FOIL. First times first is a 10. Outside pair is a negative 2i. Inside pair is a plus 5i. Put those together for a plus 3i. And then last times last is positive times negative for negative. I times I is I squared. However, remember, if this were an x squared, we'd just walk away from it because we don't know the value of x. But we do know the value of I squared, remember? It's negative 1. So this becomes a minus negative 1, which is a plus 1, which then becomes 11 plus 3i. And again, notice how we like to put that real component first and the imaginary second. Now, I'm going to use my binomial square routine as I expand this. I'm going to say first term squared. By definition, that's a 2. Twice the product. I'm taking 5i times the square root of 2, which is just simply 5i times the square root of 2, but I have to double that. And as I double that, notice it becomes 10i squared root of 2. And it was positive, so plus 10i squared root of 2. And then last times last, darn it, last times last would be 5 times 5, which is 25. But then I times I is I squared. Now, hopefully at this point you're beginning to catch on that I squared is a negative 1, and 25 times negative 1 is negative 25. So I'm going to combine that with the whole number 2, the like plus like, and get a negative 23, and then plus the 10i square root 3. On the I to the 35th power, here's the trick that you're supposed to remember. And this is a rule of exponents that we haven't talked about, but you are supposed to have mastered in Algebra 1 and Algebra 2. If I have some number at some power, and that is again raised to another power, usually they use m and n, then the final answer, I multiply the two exponents. So, as an instance, if I had 2 to the 5th raised to the second power, that would be 2 to the 10th. I multiplied the exponents together. So with that in mind, 1 less than 35 is 34. Make sure it's even, and then call this I squared to the 17th power. And remember that power of powers rule. That's why I went back to the even number before 35, so that I could take a power of I that would make the even power 34th, but still times another I. Now I squared is a negative 1, and negative 1 raised to an even power gives positive 1, but negative 1 raised to an odd power gives negative 1. So I have negative 1 raised to an odd power, that's a negative, but then that negative 1 times that I is simply negative I. Now, these last two are special forms of multiplication, and they are each called conjugates. And sometimes we call these forms a difference of squares, because that's what they create. The first times the first is 5 times 5, or 5 squared. The last times the last is simply a 3i, and that will be squared. And then the positive times the negative that you see here will make that a negative. So that's why it's called a difference of squares. Notice that the middle terms are going to drop out. The outside pair would be minus 15i, the inside plus 15i. And anytime you recognize two binomial factors that are identical except their sign, that will always happen. So the 25, the 5 squared is the 25, and the minus, always there, and the 3i squared, or excuse me, the 3i quantity squared is a 9i squared. But notice what happens. Remember, get used to it, that I squared is a negative 1. That's a negative 9 times a negative 1 that becomes a positive 9 that adds to the 25 to make it 34. the same thing happens here, but the only difference is this time that I have to deal with the square root in addition to the imaginary and everything else. But notice that the outside pair and the inside pair will be perfect opposites, and when I try to combine them, that's going to go to 0, so I don't need to even bother looking for the middle term. So I say first times first is first, 1. Last times last is going to be a minus because the positive times the negative. The I times the I is going to be an I squared, and the square root of 3 times the square root of 3 is a 3. Maybe a parenthesis around that for emphasis. Remember that I squared is a negative 1, and subtract the negative is like a positive. This becomes 1 plus 3 is 4. Crazy, isn't it? Now, remember one of those rules of radicals and fractions is that you're never allowed to leave anything in the denominator except a whole number. Well, 2i is not a whole number. And our solution is always to multiply by some form of 1. Now, just to notice, a whole number is not negative. Integers can be negatives, but whole numbers are 0 and positives. And we're never going to have 0 as a denominator. So if I multiply by I over I would get 2i squared, but then the I squared is a negative 1. And then I'm not allowed to have negatives in denominator. So I'm going to multiply by negative I over negative I. I'm going to expand on the top just with the distributive rule. And that would give me 3i minus I squared over negative 2i squared. Now, if you're forward looking, you know that I squared has an equivalent negative 1. And I was forward looking, that's why I chose the negative I over negative I in the first place. So that gives me the positive denominator. And this subtract I squared becomes subtract negative 1, opposite negative 1, positive 1. Remember that habit to develop. We like to see our real number first and our imaginary second. Now, these next three require us to remember that idea of the conjugate. And the form of 1 that I'm going to use here, and I'm going to use a parenthesis just to emphasize how the multiplication is going to unfold. Whenever you see a binomial form, two terms, in these denominators, whether they're imaginaries or whether they're radicals, we always use the form of 1 that is the conjugate. Technically, these are called complex conjugates because they are complex numbers. And we're going to do everything as a FOIL. So first times first is 3. Outside pair is 3i. Inside pair is 2i. Put them together for 5i. Last times last is plus 2i squared. Down on the bottom, first times first, 1 times 1 is 1. Outside pair, inside pair go to 0. Don't even look. But last times last, negative times positive, negative. I times I squared. Now remember those tricks, then you ought to be getting used to them now. The I squared is a negative 1. 2 times negative 1 is negative 2. 3 plus negative 2 is 1, plus the 5i. And again, the habit of putting the real and then the complex. But down on the bottom, I squared is negative 1. 1 subtract negative 1 is like 1 plus 1 is 2. So they call that rationalizing the denominator. The only thing that we want in a denominator is a whole number. We don't want radicals, we don't want fractions, we don't want imaginaries, we just want a whole number in every denominator. So on this one, the complex conjugate will be 1 minus I square root 3. And it is not a requirement to write it, but it is absolutely critical that you see it. That fraction bar, the vinculum, is a grouping symbol. And on the top, it's a distributive rule, so that I get 2 minus 2i squared of 3. But on the bottom, it's a FOIL. But specifically, it's that difference of squares where I never look for the middle term. First times first is 1. Positive times negative is negative. I times I is I squared. Square root of 3 times square root of 3 is a 3. But remember that I squared is a negative 1, so I have a negative 1 times 3 is negative 3. 1 minus negative 3 is 4. Now, you're supposed to always simplify, and the way that you simplify is always to cancel factors. So I see a two-termed expression on the numerator with a common factor of a 2. And then that would give me a 1 minus I square root 3. And then I can cancel and bring this down to 1 minus I squared root 3 over 2. That is the correct simplification. And if you don't do it, well, it's just like calling a 9/12 a 9/12 instead of reducing it to a 3/4. So last one, we're going to multiply by the complex conjugate of the denominator. So it'll be 2 plus I squared root 2. And it's always a form of 1, so it's the number divided by itself. And then on the bottom, I'm going to do it first. 2 times 2 is 2. And then the negative times positive is the negative. I times I is the I squared. Square root of 2 times square root of 2 is a 2. But up on top, I recognize that that's a binomial square. So I'm going to do the binomial square. I'm going to say square the first, 4. Multiply and double, 2 times I squared root of 2. 2I squared root of 2 doubled, 4I squared root of 2. And then square the last, which will be plus 2I squared. Now let's simplify a little bit more. I'm going to do a couple of things in my head. I recognize the I squared is a negative 1, so that 2 times negative 1 is negative 2 combined with the 4. 4 minus 2 is 2. And then the 4, oh, I said it, but I didn't write it. 4I squared root of 2. I'll try to sneak it in there. And then down on the bottom, same thing is true. The 2 times the I squared becomes a negative 2. Then 2 subtract negative 2 is 2 plus 2 is 4. And notice that the top, both terms are divisible by 2, so I'm going to factor out a 2 and have a 1 plus 2I square root 2 all over 4. But 4 is a 2 times 2. That's what's actually happened when I cancel. And those 2's cancel. And then that leaves me the simplified form, 1 plus 2I squared root of 2 over 2. Now, when something says satisfies, that's not the same thing as telling you to solve. What it's saying is that if you take the 2 plus square root of 3 in place of x, it should become a true statement, because that's the definition of a solution. It makes a true statement. So I'm going to take 2 plus square root of 3 in place of x and square it for the first term, minus 4 times 2 plus square root of 3 plus 1. And I hope it works out to 0. I'm going to put a question mark there. I hope it works. So I'm going to square the 2 plus square root of 3 by the binomial square theorem. I'm going to say it's 4 plus multiply and double. 2 square root of 3 doubled, 4 square root of 3. Square the last. Square root of 3 is the thing that squares to make 3. It squares and makes 3. Then I distribute on the second part, so I get minus 8 minus 4 square root 3. And then lastly, I get the plus 1. And I hope it works out to 0, does it? Well, guess what? Plus 4 square root of 3 minus 4 square root of 3 is 0. And if I look at the 3 positive terms, what do I get? I get 4 plus 3 is 7, plus 1 more is 8, minus 8, oh look, it worked. I get 0 equals 0, it worked. So let's do the same thing here. Let's put this value here in place of x. We'll have negative 3 minus 2i squared, so there's my x squared, plus 6 times my value of x, which I hope is negative 3 minus 2i, and then plus 13, and again, I'm hoping that works out to equal 0, does it? I'm going to square the binomial by the binomial square theorem, and square the first, negative 3 times negative 3 is positive 9. Multiply and double. Negative times negative is positive, so 3i and 2i multiplied is 6i, doubled is 12i. And notice it's positive because of the multiplication. It's not because of the I squared. And then square the second. Negative 2i times negative 2i is positive 4i squared. I distribute the 6 across and get minus 18 minus 12i. And then don't forget your plus 13, and we hope that it works out to equal to 0. Now let's just stop right here and look at a couple of things. Oh look, plus 12i here, minus 12i here. Those go to 0. The 4i squared becomes 9 minus 4 minus 18 plus 13. And we hope it works out to 0. Now what I like to do on these is to combine the two negatives. That's a negative 22. And then combine the two positives. Oh, that's a positive 22. And then combine the two answers. Oh, look, it's 0, so it checks. So that's what it means to demonstrate that it satisfies, not to solve the equation. And there's a simple way to solve both those equations that is not the quadratic formula, and that's where we're coming to very soon. Now, lastly, we see this crazy looking equation here. And I just happen to know that the square root of 3 is bigger than 1. So I'm going to subtract x to the other side and get 2 is equal to x squared of 3 minus x. And when you see this form, recognize it's a two-termed expression that has a common factor x. So that it becomes then 2 is equal to x common factor. And if I pull the x common factor out, I'm left with square root of 3 minus 1. So I guess to solve for x, I just need to divide both sides by square root of 3 minus 1. So that gives me x is equal to this expression here. And that is the correct numerical value, but recognize that we don't like that. And so I am going to express this in its more customary way. Now, one of the things to notice, I said earlier, we don't like to write anything to the right of a radical. And the reason is, if I'm a least bit sloppy, you may be unsure whether that negative 1 belongs inside the radical or outside the radical. And it belongs outside, definitely. What they do in Europe, I hear, is that they put a little tick on the square root that say, square root ends right there. So the trick, remember, is the conjugate multiplier. So square root of 3 plus 1, top and bottom. So the top is a distributive, although I'm not going to distribute it because I'm forward-looking. After all, I'm the guy that made this problem. I ought to be forward-looking. Down on the bottom, first times first is 3. Last times last is minus 1. Oh, look, that would be 2 times the square root of 3 plus 1 divided by 2. Oh, the 2's cancel. And the final result is simply the square root of 3 plus 1. Now, it's interesting if you go back and put the square root of 3 plus 1 in for x to see if it really makes that into a true statement. And I will tell you, it will. So, that was kind of a lengthy lesson. Lots of stuff. That's probably 2 weeks of Algebra 1. That's probably a week and a half of all Algebra 2, all crammed into one lesson. Boom.